Hello. So I forgot to hit record in lecture today, so what you're about to hear is a redo of lecture. So we'll get started. So we just finished chapter 6 talking about electron properties and electron configurations. Chapter 7 deals with nuclear trends and how the nuclei play a role in our trends of properties of elements. And then we'll think about how those different elements form bonds, ionic bonds and covalent bonds in chapter 8, and the shapes of molecules and bonding models in chapter 9. So chapter 7 deals with the development of the periodic table, effective nuclear charge. Nuclear charge is a symbol Z, so effective nuclear charge takes the symbol Z effective. And so this is the charge experienced by the valence electrons of atoms, or it's the charge that you might imagine a particular electron experiencing within a multi-electron atom. The effective nuclear charge is really what gives us our left to right behaviors. You look across from lithium on across to neon across the periodic table. This is going to be the main trend that takes us from metals to nonmetals with their different behaviors and trends. Our ionization energies and sizes of atoms relate to our effective charge. We're going to see that the more attracted you can make an electron to an atom, generally the smaller you'll make the atom, and then generally the higher you'll make that ionization energy. The ionization energy is the energy it takes to remove an electron. So if you take sodium to sodium plus an electron, this represents the ionization energy of sodium. The electron affinity is sort of the opposite, but not the direct opposite reaction. It's sodium absorbing an electron to go to sodium minus. Now, we don't really encounter sodium minus too often, and it's going to be because its electron affinity isn't as favorable as other elements. Like if you compare F going to F minus plus an electron, that this is more favorable for fluorine to absorb an electron, excuse me, F plus an electron, opposite side of the reaction. So F plus an electron to go to F minus. This reaction has an electron affinity that's more favorable than sodium's, and then also fluorine's loss of an electron to F plus an electron is less likely. That it has an unfavorable ionization energy, but sodium's more favorable than fluorine in terms of ionization, so sodium's more likely to want to go to sodium plus, fluorine's more likely to want to go to F minus than they are to want to go to Na minus or F plus. We'll talk about metals, nonmetals, metalloids to wrap up the chapter. We are only talking about in covering section 7.1 to 7.6. 7.7 to 7.8 are being skipped in our coverage in 1210. So section 7.1 discusses the development of the periodic table. You can see that the different shadings telling us some elements, 9 of them, were observed, detected in ancient times. Mid ages were some other elements like platinum, zinc, the phosphorus group. We're seeing some elements later. Our latest elements are the ones that are not naturally occurring, and then these ones here are the ones that are not naturally occurring on Earth, but observed in some other environments. And then other elements are kind of in the middle. Noble gases kind of later to the mix to be discovered. Um, I happen to have I didn't mention this in lecture, but I happen to have just seen a thing on Reddit yesterday on why is neon, argon, krypton, why do all the noble gases end in On except for helium? And it had to do with helium being discovered as some lines observed from the sun well before it was discovered on Earth. So it's just its discovery really had nothing to do with it being a noble gas. But anyways, Mendeleev arranged the elements by atomic weights and grouped them into categories of elements with similar properties. This was in about 1870-ish. And so this is about 30 years before the electron was discovered, about 40 years before we really started to understand the behavior of nuclei, of atoms. Moseley bombarded elements with electrons found. There's a signature X-ray from different elements. And so these sort of factors here led to the arrangement of the periodic table by increasing weight and then by grouping elements by similar properties. So you get your metals that tend to form plus charged ions most readily on the left side, and then you have things like noble gases on the far side of the periodic table. So also sharing the behavior as existing as monoatomic gases. The main difference of our elements as we go from left to right comes from their difference in effective nuclear charge. So the effective nuclear charge is charge experienced by the outer valence electron or by a particular electron in an atom. So we started our discussion with lithium. So if you imagine a 1s2, 2s2, you can sort of start to picture having the 3 plus nuclear charge, lithium's element number 3. So you have 3 protons. You have a 1s electron spinning, say, in this sort of counterclockwise direction. Then you have one other electron in this orbital spinning in a clockwise fashion. It looks like I'm running these both spin up, but really we're just having one spinning, say, clockwise, the other counterclockwise. So that's our 1s shell, and then we have a 2s shell electron here, and then our 2s1 configuration for lithium gives it its particular, size. But you can start to think of this 2s shell electron. How much of that 3 plus charge makes it out to that 2s electron? And that's what the effective nuclear charge is trying to tell us. Our Z effective is equal to our nuclear charge minus whatever the screening ability is for those 1s2 electrons. So the screening ability, this is like the screening factor. And this screening factor tends to be proportional to the number of core electrons. So if the number of core electrons increases, our screening value increases. And it tends to be equal to or less than or equal to the number of core electrons itself. So a core electron can't absorb any more charge than its charge itself. But sometimes we'll see as the core electron grows in size that its ability to absorb a full 1 plus charge for each 1 minus electron is not quite as high as the number of core electrons. And so the few sort of thoughts here, we have negatively charged particles that are repelling each other, and they're being pulled into our nucleus. I know the examples here showing sodium, but we're just imagining for now it's showing us lithium. So lithium, 3 plus charge, being sort of thinking about its attractive forces on its electrons. So for lithium, we might take an approximation and say for lithium that we can approximate our Z effective and say, well, it's going to be at most the plus 3 nuclear charge and then minus those 2 core electrons, giving us a charge of about plus 1. Okay, and so let's think about how this charge compares to beryllium, being the fourth element. So being a 1s2, 2s2, of course. And so we have a 4 plus nuclear charge. We have a 1s2, 2s2. And then we have a 2s1 and a 2s2. So we have a 1s2 and a 2s2. Okay, now I've drawn these kind of similarly sized, but if we start to think about what charge makes it out to these negative electrons here, is probably going to be a little higher. Our Z effective of bromine, or beryllium, should have a Z effective of about plus 3. Let's keep this approximately. So approximately plus 4, and then minus the 2 core electrons for being approximately now 2 instead of plus 1. And so the key is that they have the same core. In fact, the core electrons, you can think, what's going to happen to these core electrons? They're experiencing a greater charge. Those core electrons are going to get closer to that charge. And that's going to allow these 2 electrons here to also get closer to the charge because they're experiencing a greater charge. So their repulsions can be, the electrons repel each other, so they don't get infinitely as close together, but they get closer together in beryllium than they do in lithium because they're now experiencing a greater effective charge. You can start to think about a few things. You can think about the energy of electrostatic attraction, and that's kappa Q1 Q2 divided by D. This is an equation for physics known as Coulomb's law. But as we make the magnitudes of charge bigger, and we keep them minus and plus, or plus and minus, then we're increasing the magnitude of that energy of attractive force. So we get oppositely charged particles, we get attraction. And if we have obviously negative charges or plus charges, then we'd have repulsion. So we get attraction for negative electrons to the positive nuclei, but then greater attraction for beryllium than for lithium. And so what should happen for beryllium? Well, we can make a couple predictions. One is that the effective nuclear charge of beryllium should be higher. The effective nuclear charge of beryllium should be greater than the Z effective of lithium. We should be able to predict then too that this is going to play a role in the size, that this should make the radius or the size of beryllium to be smaller than the size of lithium. This allows the particles to get closer towards that nucleus of beryllium. And then three, if we start to think of the energy that's going to be required to remove these electrons from these atoms, that the ionization energy, the energy to remove that 2s electron from lithium, versus the energy it takes to remove a 2s electron from beryllium, beryllium's electron is closer to the nucleus with a higher charge. Both of those say that the energy of attraction should be greater. We have to break that attraction. So our IE1, the energy to remove an electron, that first electron from the atom of beryllium, should take more energy than the IE1 of lithium. So we can come up with these predictions just based on a really simple model of what charge these electrons in lithium and beryllium are experiencing. Now, another thing that's worth noting is that if you go from lithium to beryllium all the way across to fluorine or to neon, let's look at neon for a minute. We got a 1s2, 2s2, 2p6. That are 1s2, we still just have two core electrons, and these are all the valence electrons. And so if we get all the way across the neon, we've increased the effective charge with each successive atoms across that second row of the periodic table. Then when we get to sodium, we zoom in here and look at sodium, we now all of a sudden have a 10 electron core instead of a 2 electron core. So we like reset our core number of electrons with sodium back to 10 core electrons. And if we go to our calculation or Z effective of sodium, we would approximate as being about plus 11 protons in the nucleus, minus 10 core electrons. And we reset then with a lower and the lowest possible effective nuclear charge for the third row with sodium, and then it's going to increase across from left to right from there. So we'll summarize effective charge in a couple of slides. I think on the next slide, we'll summarize it. But what we can say is that our effective nuclear charge, what we can see is that our effective charge is increasing from left to right because our core is constant, and we're increasing the Z with that same trend. And then secondly, we can see from top to bottom that we're resetting that effective charge, and we're coming up with the lowest possible effective nuclear charge on the leftmost elements in the periodic table, and then we go back to increasing from left to right. So the effective charge is that thing that then periodically resets itself, and that's why we go from lithium on across to neon, from being metal to non-metal, and then back to sodium, back to being metallic, and resetting that periodic property. Okay, so let's summarize a few things here. So our Z effective is Z minus S, approximately Z minus the number of core electrons. And really, this is the highest that our S can be. And so S is going to be this or lower. So it's going to be the number of core electrons or less as that screening ability becomes poorer. And so S is less than or equal to the number of core electrons. Just keep this in mind that core electrons, as they become larger in size, they're not going to screen as effectively. That's going to make S a little bit smaller as we go to bigger elements. But let's talk about that in a minute. So our effective nuclear charge increases from left to right across the row. This is because the core electron count is constant. And of course, Z increases with that same trend. The number of protons, that's what's changing as we go from left to right. We got Z increasing and the core electrons being constant. But then we get a slight increase down a column. We're going to see this is because the core electrons with higher N values have a lower screening ability. So as you take a 1s2 core and compare it to 1s2, 2s2, 2p6 core, and you compare that to a 1s2, 2s2, 2p6, 3s2, 3p6 core, that as those valence electrons, you start to think of these valence shell orbitals, these core shell orbitals, getting larger in size, that their screening ability is getting poorer as they're getting larger. So the ability of a 3p electron to screen versus a 1s electron to screen nuclear charge, the 1s does a better job. the 3p electron doesn't screen as effectively. We can see that if we compare some trends on this chart here from left to right. Let's first look at the trend from lithium to argon. Notice that if you go from lithium to beryllium up here, you're just changing your Z. So the black curve is just looking at the Z, the nuclear charge. The Z is equal to the number of protons. So the number of protons just increasing from lithium on across to argon with no resetting of that trend. And then the charge experienced by the 1s electron is the red. So the Z effective for the core 1s electrons. So you said, well, what charge do the 1s electrons experience? It's effectively the full nuclear charge. You can see, like for argon, there might be a little bit of a screening of those valence electrons in the core, but it's very, very small. And you get a definite increase in our effective charge for the core 1s orbitals. So then the green curve is the Z effective using the valence electron as where S is equal directly to the number of core electrons is the green curve. And so you can see that the approximation of S is the number of core electrons is a pretty good approximation in terms of getting the trend that Z effective increases from left to right. Notice the blue and the yellow curves. The blue curve is a computational method with advanced methods, and then the yellow curve is something called Slater's rules, which I don't think is worth dwelling on. The book goes into Slater's rules being a slightly kind of way of calculating our effective charge um, uh, with an equation that's a little bit more advanced and just using S as the number of core electrons. I don't think it's super intuitive though. But the blue and the green, excuse me, the blue and the yellow kind of overlap each other, showing you that Slater's rules and these advanced methods are just a better way of calculating the actual effective charges. But notice that the green curve and the blue and yellow curves show the same trend. That Z effective increases from left to right without any periodic inconsistency, meaning it increases from left to right without any break in that trend. And so the blue, yellow, and green curves show that trend as well. If you notice, it's a little wishy-washy here, but the green curve just a straight increase, but it still increases each step of the way from left to right, whether or not you're using an advanced method or approximating your effective nuclear charge. Now, the one thing that the advanced methods can show you, compared with approximating Z as the number of core electrons, if you look at sodium, so let's orient our eyes over here. This is sodium. And so for sodium, we'd calculate +1 just like we would calculate +1 for lithium. If you notice for lithium, the +1 effective charge was a pretty good approximation because you have a 1s2 core, they're screening about the full amount of charge they can screen, which is +2, leaving behind +1. And all three methods are pretty similar in their agreement here. But if you notice, we get a little bit of a divergence between our green, blue, and yellow curves. The more advanced methods are giving you a higher charge. They're giving you a higher charge because the S value is less than +10. So the S value just isn't quite +10 for sodium because the 2p electrons and the 2s electrons just aren't as effectively screening charge as those 1s2 electrons were. So they let a little bit more charge through, but still sodium is the lowest effective charge in that group of elements or that row of elements from left to right. And it definitely increases the magnesium to aluminum on across the rest of the elements from left to right. And so even though sodium isn't quite +1, it still then resets with having the lowest possible effective charge from left to right for that next row of elements. And so then if we could go back to, the next element being potassium, again, we would approximate +1 using Z minus 18, Z minus the number of core electrons, but then we'd expect there to be a little bit more of a deviation, so a little bit of a higher true effective charge for potassium. So again, just trying to reinforce why it is that we say that the effective charge increases slightly down a column. Um, and that's because the core electrons, as you go down the column, are using larger orbitals, and those larger orbitals are not as effective at screening nuclear charge. Okay, so a couple summaries here. So effective charge Z minus S approximately equal to the number of core electrons. Now, why do the 2s and 2p not screen each other? When you're looking at, say, boron being a 1s2, 2s2, 2p1, why is it that the 2s shell doesn't really screen the 2p subshell? The answer is they're kind of in the same region of space. They're kind of fighting for the same space. They're in the same region as each other. So it's really not possible for those electrons to screen each other. it's much more easy when an electron is using a space much closer to the nucleus. If you notice the 1s shell of hydrogen using a much smaller size orbital than the 2s and the 2p subshells. And you can already start to see the overlap. The more overlap you get, the less the effectiveness of the screening of that shell. So as the core electrons grow larger in size, you're going to get a bigger overlap, less effective screening. Okay, so the core electrons screen nuclear charge from the valence electrons. Valence electrons do not effectively screen each other, and then the core electrons in larger orbitals are poorer screens than those in smaller orbitals. So as you start to use larger orbitals and bigger atoms, the core electrons are not screening as effectively. So just showing you why you get a higher Z effective than you were sort of predicting with the green curve, with that approximation Z minus the number of core electrons. So think of the core electron approximation as being the best S can be, and that as those cores are growing larger in size, that the S is a little bit lower in magnitude than being directly equal to the number of core electrons. Okay, now how does this play a role in size? We already talked about this with lithium versus beryllium. One of the things that you might compare is the non-bonding radius versus the bonding radius. And so the non-bonding radius of an atom would be its size if it weren't paired up with another atom. But if we pair atoms up, their bonding atomic radius sort of shortens. And so if we take the bond length d and take half of it, that's the bonding atomic radius. Okay, and so the bonding atomic radius, we call that the bonding atomic radius. I think I didn't so clearly say this in class, so in the actual lecture today, it was a little bit confusing, but the bonding atomic radius is going to be shorter than the non-bonding atomic radius. So if the atoms were existing without forming a bond with each other, they would be bigger in size. So the bonding atomic radius is just half of the bond length between two atoms. So you can imagine taking like experiments that tell you the chlorine-chlorine bond length, dividing that bond length by 2, and that would tell you the bonding atomic radius. And then if you knew the bonding atomic radius, that you would know the non-bonding atomic radius of chlorine would be a little bit bigger because we have electrons being shared in the bond, and those electrons being shared bring the nuclei closer together. Now the two atoms just don't sit directly on top of each other because of the repulsion of the nuclei. So the nuclei repel each other. So there's some ideal bond length here. So that's why these atoms just don't simply overlay each other, is because of the repulsion that their nuclei have with each other. And so this chart here is trying to show us the trends and some actual information we can use to solve for bond lengths of molecules. So it's trying to show us the size of atoms in compounds. And so this is in compounds with single bonds. It's a little bit tricky to sort of start thinking about single versus double versus triple bonds when that doesn't really come up in terms of predicting or sketching out Lewis structures until the next chapter. But just like the utility of this chart is we can start to predict single bond lengths in different types of bonds, but it's also just showing us the trend of bonding atomic radius. So this trend here is the size of atoms and compounds. So this is a bonding atomic radii chart. And so the bonding atomic radius trends from left to right follow the trend you would expect from effective charge. That is, you go towards a higher charge, you go to a smaller size. So we decrease in bonding atomic radius, and you would decrease with non-bonding atomic radius too with the same trend. So you decrease from left to right across a period or across a row of the periodic table because the Z effective is increasing with that same trend. So as you go lithium, beryllium, boron, carbon, the Z effective is going up, and then that's pulling those valence shell electrons in more closely. Even though you're packing more electrons in that repel each other, they're still sensing that positive charge and heading closer towards it, becoming smaller in size. Now, something kind of strange emerges in that the halogens are the smallest on this chart. Notice that the noble gases are bigger. This is kind of a nuance just because the noble gases don't form bonds like the other elements. So these are really non-bonding atomic radii for the noble gases, and they're bonding atomic radii for the others. So it's like for every other element but the noble gases, we have that shorter bonding atomic radius on this chart. And then since the noble gases aren't forming bonds, we have their non-bonding atomic radii. And so that's why it appears that the noble gases are breaking from the trend when it's really just a little bit of a nuance of the trend. So I think if you were to compare the non-bonding atomic radius of fluorine, that fluorine would still be bigger than neon. Just since fluorine though forms bonds, those bonds have a shorter length due to the sharing of electrons when you make bonds. Now, top to bottom trend is maybe exactly what you would expect. And then we just need to come back to something though to make sure we don't trick ourselves here. But we get an increase in size just because we're using larger orbitals. So as you go from a 1s1 configuration, 2s1, 3s1, 4s1, you're using larger orbitals, and you're encompassing or closing in that subshell before it. So you're just using larger orbitals, packing more electrons in. So from top to bottom, we're increasing in size just because we're using larger n orbitals. As n goes up, size goes up. Okay. Now, the only thing that we might want to come back to is that the Z effective increases from top to bottom. And you might have fooled yourself into thinking, well, if the Z effective goes up slightly, though, from top to bottom, shouldn't that cause a decrease in size? And the answer is, well, that even though it goes up, we pack more electrons in, we're using larger orbitals, and those factors overweigh the increase in the effective charge. So the effective charge does go up, but it doesn't control the trend in size from top to bottom. So we can imagine that the Z effective does increase from top to bottom, but that just doesn't play a role in predicting the size of the atoms from top to bottom. Their orbital size and number of electrons is playing a bigger role. Now, I mentioned in class, and this was a little confusing at one part, that you can actually use the chart to calculate a bond length. Like you can take the bonding atomic radius of hydrogen of 0.31, multiply that by the two atoms, so you'd predict. This is actually a bad prediction. And it was making me wonder in class if hydrogen is wrong on this chart, and it very well could be. But 0.62 angstroms are prediction for H2 bond length. The reason why I say this is I know hydrogen has a bond length closer to about 0.74 angstrom. But that aside, you can try to predict bond lengths on this chart here. Um, we did in class, we showed like if you're predicting the bond length of water, you would just look up the radius of oxygen, 0.66. So 0.66, and then we look up the radius of hydrogen, 0.31, and we can add them together to get the bond length of about 0.99 angstrom for water. So we can predict bond lengths of single bonded atoms as they connect together. And so let's look at some trends here. So sodium versus F, if we're comparing their size, so ionic or atomic radii. So atomic/ionic radii sizes. These are neutral, so these are just their atomic radii. So it's the size of sodium versus fluorine. Now, sodium is here, F is here. How do you compare their size? Well, think about lithium. That sodium is definitely bigger than lithium, and then lithium is definitely bigger than fluorine because size decreases from left to right. And so, of course, sodium has to be bigger than fluorine. We're mentioning in class that sometimes we could give you elements that are hard to compare. Like if we said lithium versus like chlorine, which one's bigger? That trend's going to be probably impossible to know because if we try to compare lithium and chlorine, lithium is bigger than F, but F is smaller than chlorine. So is lithium or chlorine bigger? Who knows? We can't really compare easily. So some elements we can't compare just based on where they're at on the periodic table. But sodium and fluorine we can compare and know for sure sodium is bigger than fluorine. If we flip back to the previous chart, you can look at the numbers and see clearly sodium neutral bigger than fluorine neutral. And that's really not even close. But then we come back to this idea that sodium plus definitely is smaller than sodium. Lose an electron off an atom, it's always going to be smaller. But if you absorb an electron in, then that extra electron is going to be bigger as well. So add an electron in, the anion becomes larger, so the anion is bigger, and then the cation is smaller than its neutral atom. And then if we're comparing sodium plus and F minus, we just have to recognize they both have 10 electrons. So we're comparing 11 positive particles versus 9 positive particles to hold the same electron count in. And sodium plus wins that fight. So sodium plus smaller than F minus. Again, this is that isoelectronic series. Isoelectronic, meaning they have the same number of electrons. I'm actually going to reverse the slides from the way I did them in class. I want to cover this slide first before I talk about a few examples of size. And so cations are generally going to be smaller than their parent atom. So if we just imagine taking something like lithium and we go from 1s2, 2s1, and we kick out this 2s1 and just go to lithium plus being a 1s2, of course lithium plus has to be smaller than lithium. And you see that here, that lithium plus is a lot smaller than lithium neutral. And so if you look beryllium neutral, lose 2 electrons off beryllium, really small, and lose another, electron, so boron 3 plus, a lot smaller than boron. And now if you go to the opposite side of the periodic table and recognize that O and F more likely to absorb electrons than lose electrons, anions though become larger than their parent atoms. So if you go and look at fluorine being a 1s2, 2s2, 2p5, and go to F minus and say 1s2, 2s2, 2p6, think about the size here for F minus. We're adding an extra electron. You add electron repulsions. The added electron repulsions, electrons repel, the size grows bigger. And so F minus is actually a lot bigger than F. So notice how F more than doubles in radius. Oxygen as well, put 2 electrons around an O atom, you get a big increase in size for O2 minus compared to O. So anions are larger than their neutral counterparts, cations are smaller. Even if you could look at like the trend of, like, let's say aluminum. So if you look at aluminum to aluminum plus to aluminum 2 plus all the way to aluminum 3 plus, spread these out better. That if you're comparing these sizes, that aluminum is of course going to be bigger, remove an electron, make aluminum plus smaller, make aluminum 2 plus even smaller, and then make aluminum 3 plus the smallest of the three. And of course aluminum 3 plus is the only stable one of the cations, so we only see aluminum 3 plus on a chart like this. And then we have magnesium 2 plus versus sodium. So notice again, in each case, smaller cations grow smaller than their neutral counterparts, and the anions of like sulfur and chlorine go bigger. Now something worth noting is, notice how sodium to magnesium to aluminum, notice how we get a decrease in size. Despite the fact if you go from, and you get the same decrease in size for their neutral atoms too, but you're going from sodium plus to magnesium 2 plus, aluminum 3 plus. These all share having 10 electrons. So they all have 10 electrons. Aluminum 3 plus had aluminum had 13 electrons. We lost 3. We're down to 10 for aluminum. Magnesium had 12. We're down to 10 for magnesium. Sodium had 11. We're down to 10 for sodium plus. Now, notice that you go from having 11 protons to 12 protons to 13 protons. 13 protons with the same number of electrons pulls them in more closely. Now compare here at oxygen and fluorine. These also have 10 electrons. Oxygen had 8, fluorine had 9, but we picked 2 up for O, 1 up for F. But we only have an 8 plus and a 9 plus. So notice that oxygen, despite oxygen atom being bigger than F atom, well, I guess we keep that same trend. So that O2 minus is then bigger than F minus. So O2 minus versus F minus, they each have 10 electrons, only 8 protons to hold in the charge for oxygen, 9 protons for fluorine, so fluorine grows smaller than oxygen. So if we were comparing O2 minus with F minus with sodium plus with magnesium plus, magnesium 2 plus, that what we can do is notice that these are all isoelectronic, meaning they have the same number of electrons. So they have the same electron configuration. So iso just means same. And then we're just going from having 8 protons to 9 protons to 11 protons to 12 protons. And then our size, we're going to be biggest here, fewer protons to hold in. So think of oxygen. So we have the 8 plus charge to hold in our 1s shell, 2s shell, and 2p shell. If we kick and have now an extra proton, we're going to pull those electrons in more closely. So F minus grows smaller, sodium plus even smaller, magnesium even smaller. So when we have the same number of electrons, we're just comparing the number of protons and thinking of how those positive protons are pulling those same electron counts in more closely. So magnesium of these four is going to be the smallest ion out of the four. And so then ionization energy is the minimum energy required to remove an electron from the ground state of a gaseous atom or ion. Don't let this word here be too confusing. We're just trying to, if we're comparing like sodium and fluorine, to not have some solid versus gas phase difference between these atoms, because sodium is obviously a solid at room temperature. We're going to compare the ionization energies for the gases losing an electron to go to sodium plus, still a gaseous ion, plus an electron. This would be the I1 of sodium or the IE1 of sodium. And this is about 495 or 6, I think it's 6 kJs per mole. It's on the next slide. And if we imagine sodium plus as a gas, losing an electron to go to sodium 2 plus gas plus another electron, this is what we call the second ionization energy of sodium. It's about 4,500 kJs per mole. It's actually a little bit higher than this. It's really high. So it's about 10 times that of IE1 of sodium because we're now removing an electron that's much closer to the nucleus. So if we think of sodium, so 1s2, 2s2, 2p set of orbitals on an 11 plus charge, and then we have the 3s. So removing this electron here takes this much energy. So it's positive, takes energy to break that negative positive attraction. And so if we think of the energy of electrostatic attraction, kappa Q1 Q2 divided by D. So we're thinking, okay, for sodium, this was about 496. And then if we go to now an electron in a 2p subtotal, notice it's a lot closer to the nucleus, so our D term is smaller. And then the effective charge that electron experiences is a lot higher. And that's going to correspond to both of those terms making the energy of electrostatic attraction higher, meaning more energy is needed to break that attraction. So ionization energies of elements are always positive, takes energy to remove these electrons. And the second ionization energy is always going to be greater than the first ionization energy. So for any element, the IE, 2 is going to be greater than IE1. We have a third ionization energy that's going to be greater than IE2. So each successive electron removed from an atom takes more and more energy. Then we can also then think, well, how is this going to compare for F going to F plus an electron? So the ionization energy of fluorine, we can think, well, for fluorine, it should be smaller. So it's also smaller, and it also experiences a higher effective charge. So the IE1 of F, we're going to predict that this should be greater than the IE1 of sodium. So we can sort of predict from left to right, we should have an increase in the first ionization energy. And so this slide here lets us compare a few things. Lets us see that 496 for sodium versus 4562 for sodium. So our I2 is higher. Notice for magnesium, I1 738. So from left to right, we see an increase in the ionization energy compared to sodium. Because again, magnesium is smaller and experiences a greater charge, so it should take a little more energy to remove its electron, and it does compared to sodium. And then its I2 isn't 4,000 kJs per mole because we're still removing a valence electron. So for magnesium, it has, so for magnesium, we have a 12 plus charge, 1s2, 2s orbital, 2p set of orbitals, 3s, 2 electrons in it. So you kick that first electron out, takes 738 kJs to remove the next electron. Remember, Mg plus is going to be smaller than Mg0. So that electron's closer to the nucleus now due to less electron repulsion, so it takes a little more energy. Kick that electron off, and then try to remove a 2p orbital a lot closer to the nucleus and experiencing a much greater effective charge, 7,000 kJs per mole for removing that electron for the third electron for sodium. So you get a huge jump in energy when you go from removing a valence shell electron to then a core electron, because the core electron is a lot closer to the nucleus, experiencing then a higher effective nuclear charge. We didn't make it the way through comparing aluminum in class for every value here, but notice aluminum is a little bit lower, but then I2 is still higher, I3 is still higher, and then you get a big jump for the fourth electron. So whenever you remove the next electron after removing all the valence electrons, you get a big jump. So, 600 to 1800 to 2700, all of a sudden, boom, up to about 12,000. So notice as you go, every successive electron takes more energy. There's no break in that trend. So it always takes more energy to remove each successive electron, and then a huge jump when you start removing core electrons. So it requires more energy to remove each successive electron, and when all the valence shell electrons have been removed, it takes a great deal of more energy to remove the next core electron. So we ended class with this slide here of saying, that the effective charge, or excuse me, the ionization energy generally increases with left to right, but has a periodic inconsistency. But it's generally increasing because the Z effective increases with the same trend. So if we're going to atoms that are smaller, a higher effective charge should take more energy to ionize, but we get this inconsistency where we zigzag. And so we'll come back next week and try to understand why we get a zigzag here in our trend for ionization energy. And then also we didn't really get into the top to bottom trend at all, so we'll talk about that next week as well. Okay, so I think I went through this a little bit faster than in lecture today. So again, I got to the end of lecture today and realized I forgot to hit record. So a little bit of a different lecture. If you had attended lecture and watched this, I think you might have gotten something from this too. And if you weren't in class today, at least you got the second draft of the lecture instead of the first draft of it. Okay, so have a great weekend, everybody, and I'll see you on Monday.